Welcome to Financial Statistics. Today we are diving into the Wiener process, the absolute bedrock of modern quantitative finance. If you have ever wondered how mathematicians and quantitative analysts model the unpredictable, chaotic movements of the stock market, you are in the exact right place. We will build this concept from the ground up. Let us begin our journey. To understand the Wiener process, imagine watching a tiny speck of dust floating in water under a microscope. It jitters around randomly, constantly bumped by invisible molecules. In physics, this is called Brownian motion. In finance, we use the Wiener process to capture this exact same idea. Instead of a dust speck, imagine a stock price or an interest rate being constantly bumped by random news and market events. This process gives us a mathematical way to describe a path that is continuous, meaning it does not teleport, but is completely unpredictable at every tiny fraction of a second. Now that we have a visual intuition, let us formalize this. A stochastic process is simply a collection of random variables changing over time. For a process to be officially called a standard Wiener process, it must satisfy three strict mathematical rules. First, it must start at exactly zero. Second, it must have independent increments, meaning its next move has absolutely nothing to do with its past moves. Third, the change in its value over any time interval must follow a normal distribution, that classic bell curve, with a mean of 0 and a variance equal to the time elapsed. Let us look at the mathematical form of our first rule. This equation simply states the mandatory starting condition of the Wiener process. The symbol W represents the value of our random process, and the 0 inside the parenthesis is our starting time. This tells us that at the very beginning of our observation, the value is exactly 0. There is absolutely no randomness or uncertainty at the starting line. If we are modeling a stock's random fluctuations, we must start counting those fluctuations from a baseline of 0 at the present moment, tracking only the changes from this point forward. This brings us to the most important defining property of the entire topic. This formula describes the increment, which is simply the change in value between an earlier time s and a later time t. The symbol means is distributed as, and n stands for the normal distribution. The 0 is the mean, meaning the process is equally likely to go up or down. The variance is exactly t minus s, the amount of time that has passed. This is crucial. It means the future becomes more and more uncertain the further out we look, because the variance grows exactly with time. Before we move on, let us see this with a concrete example. Suppose we are modeling a financial variable. We know it starts at 0, and we want to find the probability that its value will be strictly greater than 2 after exactly 4 years. To solve this, we first determine the exact probability distribution at our target time of 4 years. Using our increment formula, we know the value follows a normal distribution with a mean of 0 and a variance of 4, representing the accumulated uncertainty over those 4 years. Continuing with our calculation, we need to use standard statistical tables, which requires converting our specific distribution into a standard normal distribution. To do this, we find the standard deviation by taking the square root of our variance. The square root of 4 gives us a standard deviation of exactly 2. Next, we take our target inequality and divide both sides by the standard deviation. This mathematical operation standardizes our random variable, keeping the inequality balanced while allowing us to compare it to a universal baseline. Now, for the final steps. Our complex expression simplifies beautifully to the probability that a standard normal variable z is strictly greater than 1. Looking up z equals 1 in a standard normal table gives a cumulative probability of roughly 0.8413. Since total probability must equal 1, we subtract this value to find the probability of being greater than 1. The result is 0.1587. This means there is roughly a 16% chance our financial process will wander above the value of 2 by year 4. Now that we have used the increment formula over years, let us look at what happens when we zoom in. When we analyze the Wiener process over an incredibly tiny, almost zero amount of time, we use a special notation called the standard form. By applying calculus concepts, we can describe microscopic steps forward in time and the corresponding microscopic random changes in the process. Because the process is continuous but random, these tiny steps still follow a normal distribution, making this the perfect building block for modeling financial markets, where uncertainty grows steadily. Here is the mathematical representation of that microscopic step we just discussed. In this standard form equation, dW is the tiny random change in the Wiener process. Just like before, it follows a normal distribution. The zero shows that even over a microscopic fraction of a second, the expected change is zero. The variance of this tiny change is dt, which is exactly equal to the tiny time step itself. This confirms a crucial rule for financial modeling. If you wait twice as long, the variance of the random path exactly doubles. This linear growth of variance leads us to a fascinating geometric feature known as the scaling property. The Wiener process is fractal in nature. If you take a graph of it, zoom in on a small section, and stretch the axes, the jagged line looks statistically identical to the original zoomed out line. You cannot tell what time scale you are looking at just by its shape. Because variance grows linearly with time, the standard deviation grows with the square root of time, which is exactly why financial volatility is always quoted in terms of the square root of time. Let us look at the exact formula for this fractal behavior. In this scaling equation, C is a positive constant number, representing a scaling factor for time. The left side represents the Wiener process evaluated at a sped-up time, C times t. The right side tells us this has the exact same probability distribution as taking the original process at time t and multiplying the result by the square root of C. This mathematically proves that uncertainty scales with the square root of time rather than linearly with time itself, which is a foundational concept. To truly grasp this, let us look at a visual simulation. Here, you see the jagged path of a Wiener process, starting exactly at zero, fulfilling our first rule. As time moves forward to the right, the path wanders randomly. Notice the smooth dashed lines forming an envelope around the path? These represent the standard deviation, which, as we just learned, grows proportionally to the square root of time. This visual perfectly illustrates why predicting the exact value becomes increasingly difficult the further into the future we try to look. Let us apply this scaling property to a practical scenario. Imagine a financial analyst has a computer simulation locked at a base time of 1 month. But they need to understand the process at a future time of 9 months. We need to find a constant multiplier to make the 1-month simulation mimic the 9-month process. We start by matching our variables. Our base time t is 1 and our scaled future time c times t is 9. Solving this simple algebraic relationship reveals that our scaling factor c is exactly 9. Now that we have our scaling factor, we plug it back into our main formula. We substitute 9 for c and 1 for t. The equation now explicitly states that the distribution at month 9 is perfectly equivalent to the distribution at month 1 multiplied by the square root of 9. Simplifying this, we get our final result, 3. The analyst can simply take their 1-month simulation results and multiply every value by 3. This perfectly demonstrates how volatility scales with the square root of time. We have covered a lot of ground today. Remember, the Wiener process is the mathematical bedrock for continuous random motion, always starting at 0 with independent increments. Its changes follow a normal distribution where variance equals the time elapsed. Whether we look at microscopic standard forms or apply the scaling property, the core principle remains. Uncertainty grows with the square root of time. You now understand the fundamental tool that makes modern quantitative finance and derivative pricing possible. Excellent work.